In the course of this lecture, we have mentioned the term bathtub curve a few times. So what does it really mean? Simply speaking, it is a hazard function whose shape looks like that of a bathtub. So whether looking from the side or from the end, it kind of looks like this, and that's why the name comes from. So many types of components exhibit this sort of uh, hazard curve where we can identify three distinct regions. So there is the first region which is decreasing, and then it kind of becomes flat and stays flat for a while, and then it again starts increasing. So these three regions pertain to three distinct regimes of performance. So the first region is variously termed the break-in part, or the early failure region, product noise. So, and these come from various disciplines, but they basically mean that it's early failures, those that had some manufacturing defect, they kind of burn out very early on. In fact, a very common method of quality control is to actually identify these faulty items through some early through some tests, and they are never shipped out. The next one is we have mentioned many times, is the constant failure rate region, which is also the useful life region, where failure is random. So the random failure region, chance failure region, the outer noise as opposed to the product noise. So it's basically failure caused by external events, shocks or other sort of random accidents, which are not in the control of the manufacturer. And that is the region that we like to extend as much as possible, because that is low maintenance, that's most productive, and that has the lowest failure rate for such items. And then once the useful life nears its end, the product can still function, but then damage accumulates to the point that the longer the item survives, the more likely it is to fail. So it is clearly an aging phenomenon that kicks in, that starts showing, and that's a common phenomenon even for living organisms. When various age-related issues catch up, then the death becomes more and more likely with advancing age. So these are the three regions that we often see, and together they are called the bathtub curve. Now, through an equation, we can describe this by having different functional forms in three different regimes. We can also more conveniently describe this as a superposition of three power laws, one which is the decreasing type, one which is the constant type, and one which is the increasing type. So B1 less than 0, B2 equal to 1, and B3 greater than 1. And depends how you choose them, and how you choose C1, C2, and C3 would determine the relative importance, the relative contribution of these three behaviors to the composite hazard curve. And now we can look at some of the limiting cases. So when C1 and C3 are 0, then there is no break-in, no aging, so we have the constant failure rate, the ideal exponential time to failure. When C3 is 0, then we eliminate aging. When C1 is 0, there is no early break-in period. And when C2 is 0, then there is no chance failure, no random failure. It's either break-in type failure or aging type failure. Now, just to repeat what I said before, not every component exhibits this sort of behavior. This is idealized. Some components can even eliminate the constant failure rate regime, where after an initial break-in period, it's aging and aging and aging all the way through. For such a system, this is what the hazard function would look like.